There really is a spacecraft out past the edge of our solar system that picked up a steady, unbroken frequency drifting through the emptiness between the stars. That part is completely real. One detail is worth correcting right away, though, because it changes which spacecraft actually deserves the credit. It wasn't Voyager 2, it was Voyager 1, and the actual story of how researchers found this frequency and what it's been quietly telling them ever since is genuinely one of the more remarkable pieces of accidental science in the entire history of the mission. Stick around, because I'm going to walk you through exactly what this frequency is, how a 40-year-old instrument ended up detecting something it was never designed to find, and D, why this discovery has continued to matter years after it was first announced. And if you want more of these deep dives into real published research instead of recycled headlines, go ahead and subscribe now, because there's a lot more coming out of the edge of our solar system. To understand what this frequency actually is, you first need to understand a little about the instrument that found it, because the discovery itself was almost an accident, a byproduct of equipment built to do something else entirely. Voyager 1 carries an instrument called the plasma wave system, originally designed to detect sudden, dramatic bursts of radio emission generated whenever a shockwave from the sun slams into the surrounding plasma, the thin, ionized gas that fills the space between stars. Those shockwaves cause electrons in the plasma to oscillate at a specific frequency, and the plasma wave system was built specifically to catch those loud, sudden events. What nobody was specifically looking for was anything happening in the quiet stretches between those solar disturbances. Voyager 1 made history in August of 2012 when it became the first human-made object to cross the heliopause, the boundary where the outward push of our sun's solar wind finally gives way to true interstellar space. In the years that followed, a Cornell University doctoral student named Stella Koch Ocker began carefully examining the plasma wave system's archived data and noticed something that hadn't been specifically flagged before. In between the known dramatic bursts caused by solar shockwaves reaching that distance, there was a persistent faint signal running continuously in the background, a signal with no connection to anything happening back near the sun at all. If you're finding this as fascinating as researchers clearly did, drop a comment and let me know, because it genuinely helps me figure out what other space stories are worth covering next. Ocker, working alongside senior researchers James Cords and Shami Chatterjee at Cornell's Carl Sagan Institute, along with longtime Voyager plasma wave instrument principal investigator Donald Gurnett, confirmed that this wasn't noise or an instrument glitch. It was a genuine, continuous emission produced by the natural oscillation of electrons in the interstellar plasma itself, essentially the ambient background hum of the gas filling the space between stars, entirely independent of anything the sun was doing at the time. Their findings were published in the journal Nature Astronomy in May of 2021, under the fittingly direct title, Persistent Plasma Waves in Interstellar Space Detected by Voyager 1. Ocker described the character of the signal in refreshingly plain terms once the team confirmed what they were looking at, calling it very faint and monotone, a result of it sitting within an extremely narrow frequency bandwidth. It isn't music, and it isn't anything resembling a broadcast or a message in any meaningful sense. It's closer to what you'd get if you could somehow listen in on the natural, ceaseless vibration of a gas that's simply sitting there, humming quietly at its own characteristic frequency, the same way a wine glass produces a specific tone if you run a wet finger around its rim, except in this case, produced by charged particles oscillating in near total isolation, light years from the nearest star. Cords offered a comparison that's stuck with a lot of people who've covered this story since, describing the interstellar medium as behaving something like a quiet, gentle rain most of the time. When a solar outburst does reach that far out, he compared the effect to detecting a lightning strike in the middle of a thunderstorm, a brief, dramatic spike standing out clearly against the otherwise steady background patter. It's that background patter, the gentle rain itself rather than the occasional lightning, that turned out to be the genuinely new and unexpected discovery buried in this data. Here's why this particular finding turned out to matter well beyond simply being an interesting curiosity. Before this discovery, researchers had only one practical way of measuring the density of the plasma surrounding Voyager 1, waiting for one of those dramatic solar shockwave events to sweep past the spacecraft and trigger a detectable burst of oscillation. Those events are relatively rare and entirely unpredictable, meaning researchers previously had no reliable way to track how the density of interstellar plasma was changing around the spacecraft during the long stretches of time between one solar event and the next. Discovering that the plasma hums continuously on its own, independent of any solar trigger, changed that completely. Chatterjee explained the significance plainly at the time, noting that researchers had never previously had a real chance to evaluate the interstellar medium this way, and that Voyager could now effectively report back on the density it was moving through continuously, rather than only during the rare moments a solar shockwave happened to pass by. That shift, from occasional event-triggered measurements to a continuous ongoing signal, turned Voyager 1's plasma wave system into something considerably more valuable than it was ever originally designed to be. According to the same research team, the plasma density measurements gathered through this continuous hum revealed a large-scale density gradient extending across roughly 30 astronomical units of interstellar space, along with evidence of compressive turbulence occurring just outside the heliopause. That gradual density increase turned out to be the beginning of a much longer-running mystery that researchers have continued tracking in the years since, using the same continuous hum as their primary tool, watching the surrounding plasma density climb steadily as Voyager 1 continues its journey outward, a trend that, as of the most recent published analysis, still hasn't clearly leveled off or reversed. It's worth being honest and direct about what this frequency is not, since a title promising something rewriting physics or hinting at a mysterious transmission sets an expectation the actual science doesn't support. This isn't a signal in the sense of a message, a broadcast, or anything resembling communication. It isn't evidence of anything artificial, and it doesn't require any revision to established physics to explain. It's a naturally occurring plasma oscillation, a phenomenon physicists have understood theoretically for the better part of a century, simply being measured directly, for the first time, in true interstellar space, rather than inferred indirectly or modeled from a safe distance within our own solar system. The genuine scientific value here isn't that something inexplicable was found, it's that an instrument built in the 1970s for an entirely different, narrower purpose turned out to be sensitive enough to pick up something nobody had specifically designed it to detect, and that researchers were clever enough, decades later, to recognize what they were looking at once they went back through the archived data carefully enough to notice it. There's a broader context worth appreciating here too, because this discovery fits into a much larger pattern that's defined much of Voyager's later scientific legacy, the spacecraft's original plasma science instrument, the one specifically designed to directly measure plasma density, actually stopped working decades ago, failing not long after Voyager 1 completed its flyby of Saturn in 1980. Rather than losing that entire category of measurement permanently, the mission team found a workaround, using the electron oscillation frequency detected by the plasma wave system to indirectly calculate density instead. This continuous hum represents an extension of that same resourceful approach, squeezing genuinely new scientific value out of hardware that was never intended to serve this particular purpose. More than 4 decades after it first launched, Ocker herself captured that broader sentiment well when discussing the achievement, calling the entire result a testament to the Voyager spacecraft, and describing it as the kind of engineering gift to science that keeps on giving. That's not an exaggeration. Every additional year, Voyager 1 continues transmitting data back to Earth, across a distance so vast that a single radio signal now takes over 22 hours to complete the one-way trip. It gives researchers another opportunity to catch a solar event, refine this continuous density measurement, and extend a scientific record that no other spacecraft in human history has ever been positioned to collect, simply because no other spacecraft has ever traveled this far into true interstellar space and kept working long enough to keep reporting back. It's also worth noting that this discovery hasn't simply sat as a single isolated finding since 2021. Researchers have continued building on this technique in the years since, using the same continuous plasma hum to track the density trend surrounding both Voyager 1 and its twin Voyager 2, which crossed its own version of the heliopause in November of 2018 at a completely different location in the sky. Voyager 2 still carries a functioning direct plasma instrument, unlike its sibling, giving researchers an independent way to cross-check whether the trends detected indirectly through Voyager 1's hum genuinely reflect real conditions in the surrounding interstellar medium, rather than some artifact specific to one spacecraft's particular instrument or location. That comparison has continued to confirm the broader pattern. Plasma density climbing gradually as both spacecraft travel farther from the heliopause, a trend researchers are still working to fully explain, using data. This original 2021 discovery first made it possible to gather continuously in the first place. So what does all of this actually add up to? A humming, persistent frequency really is drifting through the space just beyond our solar system's boundary, and Voyager 1 really did detect it, using an instrument that was never specifically built to find anything like it. But the honest version of that discovery is a story about clever, resourceful science squeezing new insight out of 40-year-old hardware. Not a mysterious transmission or anything that requires physics, as we understand it, to be rewritten. If anything, that honest version is more impressive than the mysterious one, a spacecraft built with 1970s technology, drifting further from Earth every single day, still managing to teach researchers something genuinely new about the nature of the space between the stars, simply by continuing to listen carefully to a signal nobody thought to look for until decades after launch. If stories like this one, grounded in real published research and honest about what was actually found, are what you want more of, subscribe to this channel and turn on notifications, because Voyager is still out there, still humming along, and there's a real chance the next few years of data reveal exactly where this quiet, steady trend is finally headed. Thanks for watching, and I'll see you in the next one.